Okay, so this is our last lesson in chapter 9. Tomorrow you have a quiz on chapter 9. I sent an email out this morning about that. Told you guys Friday. But also on the board, I've also written that Friday, June 9th is the last day for you to hand in any missing assignments. That's actually a PD day, but you can still email assignments to me and I can print them off and mark them that way. So that's the last day to hand in any missed assignments. Okay, after that, all the blanks in Power School will be changed to zeros and your marks will go down. I would recommend that you start working on that sooner than later so that you're not under the gun come June. So we've been learning about graphing rational functions, the different characteristics of these rational functions. Some of them have vertical asymptotes, some of them have points of discontinuity, some have horizontal asymptotes. We even see some that had what's known as a slant asymptote, which you don't have to figure out what that slant asymptote is, but just remember that it was there when the degree of the top was one more than the bottom. Right? So now we're going to look at solving some of these rational equations. The first question says determine the roots of the rational equation x plus 6 all over x plus 2 take away 5 equals 0 algebraically. There have been questions on diploma exams on written response where they'll ask you to solve an equation, determine the solutions to an equation, which again means you have to show all your work. That's what the word determine means. Show your work as to where you got your answer from. So in this case here, to solve that equation, the best thing to do is to get rid of the denominator by multiplying every term by the common denominator, because there is only one denominator that will be your common denominator. So this is showing that I'm multiplying all the terms by the common denominator, which is x plus 2. And technically you're multiplying the right side by x plus 2 as well, because the right side is 0. 0 times x plus 2 is still 0. The whole reason we do this is so that the x plus 2's will cancel on the term that's actually a rational expression. That's why we use this step. So multiplying everything out, you'll get x squared plus 2x plus 6 minus 5x minus 10 equals 0. Or x squared minus 3x minus 4 equals 0. We've got a quadratic. We can solve that by factoring. X minus 4x plus 1 equals 0. And your solutions will occur where each factor equals 0. So where x plus 1 equals 0, we get an answer of negative 1. Where x minus 4 equals 0, we get an answer of positive 4. And whenever we solve equations, we always want to check to make sure what works, what doesn't work. If something doesn't work, then it's an extraneous solution. So first for negative 1, you'll get negative 1 plus 6 over negative 1 plus 2 is 1 minus 5. Negative 1 plus 6 is 5. Minus 5 equals 0. So that one works. Checking positive 4. So when x is 4, the denominator 4 plus 2 will be 6. That's going to be 4 plus 1, which is 5. Take away 5, which is also 0. So they both check. Right? Both solutions work. Then part B says graph the rational function and determine the x-intercepts. So y will equal x plus. Now we're going to have to use brackets to keep our rational expression together. as well as brackets to keep our denominator together. So two sets of brackets there for that rational expression. One for the full expression, one just for the denominator. Zoom 6 sets their windows to their standard settings. We want to find the x-intercepts. If we go into the trace mode, it looks like one of them is at -1. Try that again, -1. And it is because y equals 0 there. It also looks like +4 is an x-intercept. And it is because y equals 0 there as well. If you can't pick the x-intercepts by looking at the graph, you can also go second function trace. Number 2 for 0. That's another name for the x-intercept. Just state your left and right boundary. And the graph and calculator will find it for you as well. But we see that the x-intercepts are the same thing as the solutions to the equation. So the connection between the roots of an equation and the x-intercepts of the functions, they are the same. When you're asked for the roots of an equation, you're asking for the x-intercepts. The roots are the solutions to the equation, the values of x that make y equal to 0. They're called the solutions, they're called the roots, they're called the zeros. They also are the x-intercepts. Number 2 says, solve the equation graphically expressed to the nearest hundredth. So sometimes the solutions are irrational. And so if you're doing it on the calculator, they have to be rounded. In this case, we have a left and a right side to the equation. So y1 is where I'll put the left side. And again, we'll need to use brackets to keep the numerator and denominator together. The right side will just be x minus 1. That's equation 2. And now we're going to find the points of intersection between these two graphs. So second function trace, number 5 for intersect, enter, enter, enter. So to the nearest tenth, that'll be at negative 0. Actually, to the nearest hundredth, negative 0.43. And then the second one, put my guess at positive 3, and it's 3.097. So we round that to the hundredth, it'd be 3.10 approximately. Now, just because the answers are irrational doesn't mean that they can't be found algebraically. So we will solve this algebraically by, again, multiplying both sides by the common denominator, because there's only one denominator. 3 minus 2x, that is my common denominator. So again, this step shows multiplying both sides by the common denominator. And the whole point of doing that is so that the 3 minus 2x's cancel on the left side. So we've gotten rid of our denominator. Now we're going to solve the equation that we have left, which is going to be a quadratic that we're going to make equal to 0. But first we're going to have to multiply out that right side and then collect all the terms. So it'll be minus 2x squared and positive 3x and positive 2x and minus 3. So if you add the 2x squared to both sides, you'll get 3x squared on the left. You're going to subtract 5x from both sides because that's what 3x plus 2x becomes. Negative 3x take away 5x is minus 8x. And then adding 3 to both sides. gives us that quadratic to solve. And this one cannot be factored. And so we would use the quadratic formula. Negative b plus or minus the root of b squared minus 4ac all over 2a. And again, this is on the formula sheet. It's at the very top of the formula sheet, so you don't have to memorize it. It's there for you. And you can use it to solve any quadratic. Normally, if a quadratic is factorable, that's the easiest way, but you could still use this to solve a quadratic that is factorable, and we can use it to get the exact roots for a quadratic that's not factorable. So remember your coefficients of the x squared, the x, and the constant term is where those values of a, b, and c come from. B is negative 8, so negative b will be positive 8 plus or minus the root of negative 8 all squared is 64 minus 4 times a, which is 3, times c, which is negative 4, all over 2a. 2 times 3 is 6. So the discriminant, which is the number under the radical, we can find out what that is by going 64 minus 4 times 3 times negative 4. That's 112. And see, this is the reason why your answer is irrational, because you get a non-perfect square under the radical. Now it can be simplified. You can break down root 112 because it's divisible by 4, which is a perfect square. Looks like it would also have been divisible by 16. Yeah, 16 times 7 will give you 112. So if you break this down to 8 plus or minus root 16 root 7, because the square root of 16 is 4, and this allows you to divide all the terms by 2. And this just simplifies the expression. Those are the exact solutions. And if you plug these into your calculator, you're going to get that negative 0.43 and the 3.10 value that we got on or from the graph. So again, we need to use brackets to keep numerator and denominator together. Let's go 4 plus 2 root 7 first. All in brackets divided by 3. So there's that 3.09716 that we got. And then the 4 minus root 7 all over 3. There's where the negative 0.42 came from. Right, so we were able to state the exact answers, which match the decimals that we found using our graphing calculator. Okay, so we see now that we can solve most of these graphically and algebraically. So this first one we want to do, again, graphically, round to the nearest hundredth. So it's 2 take away 3 halves x, which we can write as 1.5x if we want, because 3 over 2 is exactly 1.5. For the right side in equation 2, we'll have to use brackets. 1 plus 4x minus x squared in brackets divided by 4x plus 10. The graph looks like 2 points of intersection. Second function trace, number 5 for intersect, enter, enter, enter. So 1.1 4 if we round to the nearest hundred. And the other one, second function trace, 5 for intersect, enter, enter. I'll put my guess at -5, and it's actually -3.34. Again, the reason these have to be rounded is because the answers are irrational, because if we use the quadratic formula to simplify or to evaluate the roots, we're going to get a non-perfect square under the radical. Before we get there, we have to take the equation and multiply all the terms by the common denominator. Now, the one denominator, 4x plus 10, has a common denominator of 2. So that means the denominator for 4x plus 10 is 2 bracket 2x plus 5. We also have a denominator of 2 on another term. This tells us that our common denominator would be 2 bracket 2x plus 10. Our common denominator must contain the factors of all the denominators. So the fact that we have a factor of 2 for the denominator 4x plus 10 means that when we write that as our common denominator, that'll take care of that other denominator of 2. Our common denominator is 2 bracket 2x plus 5. So the first term is 2, which is multiplied by the common denominator. The second term of 3x is multiplied by the common denominator. And the other side is also multiplied by the common denominator. And the whole point of doing that is so that we get rid of all the denominators. Now this 2 here must be canceled with the factor of 2. You cannot cancel the 2 on the 2x plus 5. You can't cancel part of a binomial. Can't do that. You can only cancel factors. So, by canceling out the common factors, we've gotten rid of all of our denominators. We can now multiply out what's left. So 2 times 2 is 4, times 8x plus 5. 4 times 2x plus 5 gives us 8x plus 20. Then you're going to multiply -3x times 2, which is times 2x, which is -6x squared. -3x times 5 is -15x, equals -x squared plus 4x plus 1. So now we'll collect all the terms over to the left. I'll add 6x squared to both sides, which will give me 5x squared on the right side. On the left, I've got 8x, take away 15x, which is -7x, which we add to both sides, which will give us positive 11x. Over on the right side, and we have a positive 20 that when we subtract that from both sides, we'll get -19 equals 0. And again, this cannot be factored. So to solve it, we need to use the quadratic formula. So b is positive 11, so negative b will be -11, plus or minus the root of 11 squared is 121, minus 4 times a, which is 5, times c, which is -19. All over 2 times a, which is 10. And when you figure out the discriminant here, (121 minus 4 times 5 times negative 19 is positive 501. Which I think is a prime number. Obviously, it's not divided by 4 because it's not an even number. Let's see if it's divisible by 9. No, not exactly. Wouldn't be divisible by 16. Wouldn't be divisible by 25. I think it's a prime number. And it doesn't really matter because you can just use your calculator anyways. Go negative 11 plus the root of 501, all in brackets, divided by 10, gives us 1.14 as one solution. And then changing the positive to a negative in front of the radical is this negative 3.39. 39 or 34? 34 to the nearest hundredth. And the nice thing about the graphical part is it actually shows that both answers work, that there is no extraneous root there. But this next one does have an extraneous root. We're asked to do it both algebraically and graphically. So to do it algebraically, the denominator on the right, again, there's a common factor of 2. You've also got a denominator of 2x plus 5 on the first term, which is one of the factors of the denominator of the last term. Our common denominator here will be 2 bracket 2x plus 5. So this shows multiplying every term by 2 bracket 2x plus 5. And the whole point of doing that is so that we can cancel factors that are the same on both the top and bottom. So x times 2 is 2x plus 4x times 2x is 8x squared. 4x times 5 is plus 20x. And on the right side, we're just left with 8x plus 15. And then we bring everything over to the left side. 2x and 20x is 22x. Take away the 8x is positive 14x. And then subtract the 15 from both sides. So there's the quadratic that we need to solve. And this one can be factored. The front terms multiply to get 8x squared, so 2x and 4x. The last terms multiply to get negative 15. This will work with the positive 5 and the 2x and the minus 3 with the 4x. Front terms multiply to get 8x squared. The outer factors are negative 6x. The inner positive 20x. Negative 6 plus 20 is positive 14. And the last terms multiply to get our negative 15. So our solutions would come where each factor equals 0. And so those are the answers that we get. And we always need to check our solutions. You can check them algebraically like we did at the start. It can also be checked graphically though. So y1 would be the left side, which we'll need to use some brackets. One set to keep that rational expression together, the other set to keep the denominator together. So y1 is the left side, y2 would be the right side. And it doesn't matter whether you use the factored form or the original expanded form, doesn't matter for the denominator. Both equations are in there, and we want to find the point of intersection. Second function trace, number 5 for intersect, enter, enter. So the first answer I got was negative 5 halves, or negative 2.5. I'm going to put that in as my guess. Doesn't work. Because negative 2.5 is actually a vertical asymptote, right? Because we have a denominator of 2x plus 5. Our non-permissive values come by making the denominators equal 0, where you have a variable. And if you let 2x plus 5 equals 0, you're going to get x equals negative 5 over 2, negative 2.5. So these two graphs can't intersect at negative 2.5. Negative 2.5 can't be a solution because it's a non-permissive value from actually both denominators. So this one definitely doesn't work. So we can cross it out. We can say negative 5 over 2 is extraneous. It's a non-permissive value. But let's confirm 3/4. Second function trace, number 5 for intersect. Enter, enter. I'll put my guess at 1. And we do get, whoops, let me try that again. X over 2x plus 5. Oh, there's my mistake. It should be 8x plus 15. I got 8x plus 5. It's not going to change our negative 2.5 not working though, because that was a numerator, not a denominator. So now when I graph second function trace, number 5 for intersect, enter, enter, I put my guess at 1, and there we get our 0.75. So that point does work. The negative 5 halves is extraneous. So we want to do the same thing with this. If we take 2x minus 6, there's a common factor of 2 there, which gives us x minus 3. Now that's not the same as 3 minus x. In fact, they are opposites. If you take a negative 1 out of there, you will get x minus 3. So by doing that, it helps us get our common denominator in simplest form. Our common denominator would be negative 2 bracket x minus 3. Okay, you got to have a negative sign because one of the factors is negative 1. So we're going to multiply every term by negative 2 bracket x minus 3. And when I write my denominators, I will use the factored form. It just makes it easier to cancel. So on the right side, we have a factor or a term of 2x that will have to be multiplied by negative 2 bracket x minus 3. And again, just to help with the canceling, I'll write the denominators in their factor form. So the 2's cancel straight with that negative sign there, and the x minus 3's cancel. Over here, the negative signs cancel, and the x minus 3's cancel. So we're left with negative 1 times x plus 3. 2x times negative 2 would be negative 4x, times x is negative 4x squared. Negative 4x times negative 3 is positive 12x. And you're going to have negative x times 2 minus 2x. So if I add the 4x squared to both sides, 12x, take away 2x is 10x, which if I subtract from both sides gives us negative 11x over on the left side. And then we have the minus 3 equals 0. So there's our quadratic, which again is factorable. In this case, it'll be 4x in the first bracket, x in the second bracket. They multiply to get 4x squared. The last terms have to multiply to get negative 3, plus when you multiply the outer and the inners, you need to get a minus 11x. This will work if you put a plus 1 with the 4x, a minus 3 with the x. The front terms gives you 4x squared. The last terms gives you negative 3. The outer products are negative 12x, the inner positive 1x. They become our negative 11x. So our solutions come when each factor equals 0. So negative 1/4 and positive 3 is what we get. Now, if we look at our equations, especially the factored forms, you can see that 3 is a non-permissive value. You've got factors on the bottom of x minus 3. X can't equal 3. It's a non-permissive value. It would be a vertical asymptote. So we can already say that x equals 3 is extraneous. Negative 1/4 is not a non-permissive value, so it very well could work. And you have two ways to figure out if it does. You could plug it into the original equation and make sure you get the same thing on both sides, or you could do this graphically. So y1 will be the left side, which I'm going to have to use some brackets to keep my numerator and denominators together. X plus 3 all divided by 2x minus 6. And for the second equation, again, I'm going to have to use brackets to keep my rational expression as well as my denominators together. Second function trace, number 5 for intersect, enter, 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 and there we get our negative 0.25. Confirming that that is a solution that works. So when they talk about comparing the solutions using each method, I mean, the algebraic one takes longer for sure. It also gives you an extraneous root, where the graphical one tells you that there's only one answer that works. In this case, because the answer is a terminating decimal, negative 0.25, you could state the exact value from the graph. But as we've seen earlier, that's not always the case, right? Because sometimes these solutions are irrational, which means to write them as exact values, you need to get a quadratic and then use the quadratic formula. So page 465, questions 2 through 4 is what you should work on. I will post those to the classroom so that you can check your answers. Remember, the assignment from last class is due for marks. Also, reminder that tomorrow you guys have your Chapter 9 quiz. As well, I've written on the board that Friday, June 9th will be the last day to hand in any missed assignments. After that, they go in as zero, so you might want to start working on those to get caught up so you don't aren't so rushed come the beginning part of June.